Hello, everyone. Today we're going to talk about the confidence intervals for the mean. So if we are trying to estimate a population mean, it is rare that we want the estimate, the unknown value of a population mean, but somehow know the standard deviation. So we don't know the mean. There's going to be a really small chance that we're going to know the standard deviation, because if we knew the standard deviation, we probably already knew the mean. So it's not that likely. So something you'll notice I say here a lot is going to be sigma is not known, meaning the standard deviation is not going to be known. So the methods we're going to use for the next couple lessons, we're going to use this assumption. We don't know the standard deviation, so we have to do things a little bit differently. All right, so let's define what a point estimate is. The sample mean x bar is the best point estimate of the population mean mu. Because even the best point estimate gives us no indication of how accurate it is, we use a confidence interval, which is a range of values, instead of a single value. And then a confidence interval. Let's look at the key elements of a confidence interval. For now, that sigma is unknown. So we kind of saw it with proportions. We knew the standard deviation, a little bit easier to deal with. But now we're going to say we don't know the standard deviation. And this is probably the more accurate case here. A lot of times we'll have to use this method with sigma unknown. All right, so let's look at this little nice step-by-step guide we have here. So again, key point, this is when we're going to assume that sigma is not known. So our objective is to construct the confidence interval used to estimate a population mean. Our notation is pretty similar. Mu is population mean, x bar is sample mean, s is sample standard deviation, n is number of sample values, and e is our margin of error. So seen all of that before. And then we have two requirements we need. The first is that the sample is simple random sample. Okay, it needs to be a random sample, it needs to be a simple method, which most of the time we're just going to assume that part. We're not going to go into too much detail on the sampling methods, but we can't use any crazy sampling method for this test to work. And then the second requirement, which is a little bit more important, is either or both of these conditions are met. The population is normally distributed, so we have to somehow plot all of the data and then look to see if it's bell-shaped. Or the easy case, if n is greater than 30. We could also use our quantile plot if we get the straight line if n is less than 30. But most of the time we hope n is greater than 30, and then we don't have to worry about it. But if not, we're going to either use a histogram or quantile plot. All right. And now the actual confidence interval. We're going to format this as x bar minus the margin of error, and then x bar plus the margin of error. And then the mean will be somewhere in the middle of those two ranges. And margin of error e is we're going to use a critical t value times s divided by the square root of n, and we're going to use degrees of freedom here of n minus 1. And degrees of freedom we'll see in a second. It's a method we'll need to understand to use our chart, but it's very simple in this case. You're just subtracting 1 from whatever our n is given. For the confidence level, the confidence interval is associated with the confidence level, and this is the same as before. It's either 95%, sometimes 90, sometimes 99 if needed. If we have a 95% confidence interval, that makes alpha 0.05. It's just 1 minus whatever the confidence level is. Right. So this critical value, t with the subscore of alpha divided by 2, it's the same thing as with the z. It's the critical value, but now we're going to call them t values, separating an area of alpha divided by 2 into the right tail of the student t distribution. So we're going to take let's say if alpha is 0.05, we want 0.025 on both sides still. So alpha divided by 2. That's where that's coming from. And then degrees of freedom, is whatever n is minus 1, as we call the degrees of freedom, and this is the number used when finding the critical value. We have also what is called the round-off rule. For the original data, when using an original set of data values, round the confidence interval limits to one or more decimal places than is used for the original data set. For summary statistics, when using the summary statistics of n, x bar, and s, round the confidence interval limits to the same number of decimal places used for the sample mean. So just a little bit of notation and rounding there. Okay. So let's try and estimate a population mean now. So we need the requirement of normality, or n greater than 30. So again, if n is greater than 30, we're all set. Otherwise, the distribution should be close to being symmetric. So we look at our histogram. If it's symmetric, we're all set. We should only have one mode. The frequency that's the highest should be in the middle. And then the sample data should not include any outliers. And interpreting the confidence interval, when interpreting a confidence interval estimate, we know the confidence interval gives us the success rate of the procedure used to construct the confidence interval. So same idea as before. Let's say we choose 95% confidence interval. We would then be able to interpret that as we are 95% confident that the interval for, in this example, from 8.5901 grams to 9.0213 grams actually does contain the true value of mu. So our confidence percentage that our true value of our mu is between that range. Okay, so I've been talking about this t-distribution, but I didn't really say what it was. We know what z-distribution is, and similarly, we're going to have the t-distribution. So this is a little different of a chart to read that we'll see in a second, but we have a t-distribution, and this is if a population has a normal distribution, then we're able to use this equation of t equals x bar minus mu divided by s divided by the square root of n. And this is a student t-distribution for all sample sizes of n. So all of our given values here, and we use a t-distribution when we're using our means. So we also need to understand degrees of freedom, which will, when we see our chart, that will make sense. For degrees of freedom, we'll use n minus 1. Okay, but we're going to put a pause on that until we get to the chart for this example. So let's look at this example with peanut butter cups. So listed below are weights and grams of randomly selected peanut butter cup miniatures. They are from a package of 38 cups, and the package label states that the total weight is 340.2 grams. The 38 cups have a total weight of 340.2 grams, and the cup should have a mean weight of 8.953 grams. Okay. We're going to use the listed sample data to find the point estimate of the mean weight of Reese's Peanut Butter Cup miniatures. And we're going to use the listed sample data to construct the 95% confidence interval estimate of the mean weight of Reese's Peanut Butter Cups. Based on the preceding results, does it seem that the packages are being filled so the total packing weight is 340.2 grams? Okay. So we have our sample data here in the bottom. So these 6 numbers. And we're going to want to answer these 2 questions. So we have some of our information in here. So they're a package of 38 cups. And the package says it's 340.2 grams. The 38 cups have a total weight of 340.2 grams. Then the cup should have a mean weight of 8.953 grams. Let's see how accurate it is from our sample. So let's start with our manual calculation. So the point estimate of the data is the sample mean, which is 8.8057. the manual calculation, if we first find the critical value of t.025, it's 2.571, which we can see from our t-table using n-1 as our degrees of freedom, which would be 5. We have 6 data points. n-1 would be 5. So we have 5 for degrees of freedom. And find the standard deviation, S, which is 0.2054 from the original sample values. Now we find the margin of error. So something like this, to find the standard deviation, you have 6 values, so you could do it by hand, but might be easier just to use a technology tool there. Let's go to our table for a second. I threw all these numbers at you, but let's actually see where they come from. So we'll go back and forth between the two slides. So I gave you these numbers, but what do they really mean? So we have this critical value that we need of 0.25, which is 2.571. So how do we find this 2.571 without me just giving it to you? So if you use technology, which we'll see a bunch of technological tools that we could just find this number. There's a bunch of calculators online, just T calculators. That's one way to find it. But if we want to use our table, we're going to start by using our degrees of freedom. So that's the left column. So however many the sample is, which our sample is 6, we subtract 1. So we're going to look at the the row with 5. But then we have to match up what we're looking for. We want T of critical value is 0.025. We want to find 2.571. So here's 0.025, and then we match it up. We should get 2.571. And this table is nice. It actually gives it to you, the 1 or 2 tails, meaning 1 tail is what we're looking for. But since we want a 95% confidence interval, that's where that 0.05 is coming from. But we're doing 1 tail, so we just divide that number by 2. So you can see it either way. But that's where our value of 2.571 is coming from. So I'll post this t-table on Canvas, but this is also something you can just Google very easily. Google t-table, and multiple different versions will pop up. Okay, so now that we know this critical value, we know our degrees of freedom, we can find the standard deviation. I don't want to spend time finding that standard deviation, so I'd recommend just using a piece of technology. We could use SPSS to find that value of S, or any standard deviation calculator, or use our graphing calculators to find that value. And then we're going to plug it in for margin of error. We'll do this part. So our critical value we found from our table, that's this 2.571. We plug in our standard deviation and our square root of n. We multiply, and we get 0.215589. So now we have everything we need now that we know E. We know our sample mean. We now have our margin of error. So once you know the mean and margin of error, the confidence interval is just the mean minus the margin of error, the mean plus the margin of error. Okay. And then we're going to go ahead and round that to 4 decimal places when we add and subtract. So we'd have our value, our estimate of our true value is somewhere between this range of 8.5901 and 9.0213. So we have a 95% confidence. Our true value of the mean is somewhere in that range. Right. Actually, let's go back to the question for a second. So we have so use the sample data to find the point estimate of the mean. So that's that first number that I gave you. That's just easy. We add the numbers together, divide by 6. That's where we get this. So it's 8.629 plus 8.689, add them all together, divide by 6, because we have 6 pieces of data, just our basic mean there. Okay? And then this part is where we got our confidence interval. But we didn't answer the exact question, so let's just be careful. Based on the preceding results, does it seem the packages are being filled so the total packing weight is 340.2 grams? So for it to be 340.2 grams, the mean weight would have to be 8.953. And 8.953 is in our range here. So we would have 95% confidence that it is the case. So it is good with 95% confidence. Okay, let's look at another example now. So straight from our book here, so something we might see on the homework. So listed below are sales of vinyl LP units in the United States. The sales numbers are listed in order by year, beginning with 1993. We're going to use the listed sample data to construct the 95% confidence interval estimate of the population mean. Then we want to answer, is the confidence interval method described in this section a good tool for gaining insight into the nature of the sample data? And then lastly, apart from the confidence interval, is there other tool that would be better for gaining insight in the nature of the sample data? What is the most notable about the sales numbers? Okay, so I put our little sample at the bottom, and this is sales in millions, so 0.3 million, 0.6 million, 0.8 million, so on. And the sales numbers are listed in order, and 1993 would be that first value. So our confidence interval here would be 2.02 to 5.92. So, little mini assignment. I want you to check this. You knew this 2 different ways. If you want to do it by hand, like I did on the last example, you can do it that way. Or you can try using SPSS. Find the confidence interval using that technology. Or if you want to try another piece of technology, you're welcome to, but we will see something similar using technology or using SPSS. Here, since n is less than 30 and the data set does not appear to be normal, it's not going to be a good tool. So I'm not going to find this confidence interval because I can see that this data is not normal. So that's why I didn't write out all our computations here. So just because the question says we want to construct our confidence interval, it might not mean anything. If the data is not normal, those numbers don't have any, those t-chart numbers we have don't have any meaning because those are for normal distributions of data. So we can find confidence intervals for anything. The number just might not have any meaning. It's not very helpful. So did it a little out of order here. That's why we check. So I always recommend checking first. So n is less than 30. So we're not good to go. We have to graph this in some way. The data would not appear to be normal. So if you made a histogram, let's say, it wouldn't be bell-shaped. Looking at the data, you can kind of see that it wouldn't be bell-shaped because we have multiple of the same modes. I have 2.9s, 2 1.1s. Have any other repeating numbers? We have some 1.4s, 3 1.4s, 2 1.2s. Yeah. So we actually do have one mode, I believe. I don't see any other repeating numbers. But if we were to plot these all out, we definitely would not have a normal distribution. So always check first you have a normal distribution, because if you don't have a normal distribution, we don't really care about the confidence interval. And thinking of the context of the problem, we're talking about change over time. Our first data point's from 1993. We have the sales listed from 1993. So instead, let's use a time series graph. We want to look how things change over time. So there's a clear trend of vinyl record sales. They're going up over time. But the confidence interval doesn't really show that. It doesn't give us any insight. So it's not a helpful tool when it's not a normal distribution. So you can always find that value, but make sure it has some meaning too. Okay, next time we're going to talk about what is called hypothesis testing. Have a great day, everyone.